Okay. All right. So in today's class, okay, again, let's see, we have most of you here. So let's get started. In today's class, we're going to talk about another approach. We're going to describe another approach of designing digital systems. Okay. And but before we actually do that, let me recap what we have done so far through the semester, because that will keep things in perspective. Okay. So let's actually do that. Let's get started with that first. So what we have done in the initial step was we came up with techniques to design simple modules, small modules containing 4 inputs and so on. The simple modules can be designed by using at the fundamental gate level. Okay, design of simple modules or simple circuits or modules, short modules at the fundamental gate level. So that was how we started out, right? And of course, the approaches that we have looked into were, of course, the K-map approach, right? And or the Boolean algebra approach to come up with a function and obtain and design or construct these modules. Okay. Now we realize that that's not the only way that we can design digital systems, and of course, that's in fact that's not the preferred way of designing more complex modules. We quickly realized that in the design of your binary adder, right? And a better way to designing your digital systems, binary adder, right, was to actually apply the modular approach, where you design simple modules using the K-map approach that you already know, and then you work with those modules to build more complex logic, right? So the approach that we have taken for the binary adder was to design simple modules like you do in the first step. For example, in this case, we designed a 1-bit full adder module, and followed by that, we basically utilized these 1-bit full adder modules, many of those, to construct an n-bit adder module. And of course, we extended the concept to actually make this into an n-bit adder slash subtractor slash comparator, right? Conditional checking as well, comparator. So we could do all of these functionalities with this modular approach. So that was the second way of thinking, okay, a different way of thinking. Now, the third way, again extending from this concept, was to apply pre-made modules, modules that you're not designing by yourself, but these are available, okay, as pre-built modules that you can actually buy off the shelf, if you will, and map your function to those modules or utilize those modules to build your function. And this is exactly what we have done for the design of the BCD adder. And this is exactly the approach I suggested that you would follow for the design of your ternary adder. Right? In this case, we designed this BCD adder by using pre-made full adder modules. Like for a BCD adder, we actually used pre-made 4-bit full adder modules. So these are the modules that you can actually buy as a slice, as an IC, as an integrated circuit, and utilize that in your design, right? So here you are, in all of these techniques, of course, at the fundamental level, you're still relying on the fundamental gates, because each module at the end of the day is still composed of these fundamental gates, right? So the only different thing that you're doing is when you're working with these pre-built modules, you're obtaining the what do we call them, the gate level functionality, if you will, obtaining the gate level functionality from these modules. You're not directly accessing the gates, right? When we are dealing with the BCD adder, you really not accessing the gates within the module, but you're obtaining the gate level functionality from the modules, okay, by cleverly designing your function, by cleverly mapping your function on an existing module. I hope that makes sense. All right. Okay, so these are the three approaches that we have taken. Now, in today's class, we will extend that approach and see the design. So, in this class, we'll talk about design with the medium scale integrated circuits. Medium scale integrated circuits. What does that mean? Now, if you go back to the first class where we described, where you actually, where I shown you the image of a computer that was in the 1940s, where the computer occupied the entire room and so on, right? And we described the revolution in terms of miniaturization and what led to that revolution, right? And what led to that revolution was the invention of these techniques to integrate circuits on a same chip, if you will. Okay, so that's the integrated circuit technology that led us to the revolution in miniaturization of your logic circuits. Okay, all right. So integrated circuits, basically, that's a planar technology where you fabricate one plane by plane or layer by layer these devices and interconnect them to form your entire logical circuit. Okay, now, for example, your microprocessor, that's a planar technology that's basically done over an entire wafer, a large silicon wafer, silicon crystal, like a single crystal silicon wafer, which you will learn more about in your subsequent classes. Okay, and so you're packing millions of or billions of these transistors on the same chip, okay, on this microprocessor, and you're building up layer by layer, okay, and making your entire circuit. So the smaller the components that you can make on this chip, the more compact your system would be. The more compact and more functional your chip would be. Okay. Now, so there was, again, things did not happen overnight, right? Even with the development of the integrated circuits, we didn't start from the day one putting billions of transistors on the same chip. That did not happen on day one, right? So there was an evolution in terms of how this integrated circuit technology developed. Okay, and we can classify the integrated circuit technologies based on how many gates, how the gate level functionality that these integrated circuits can provide. Okay, and this was how the classification was done. So we can classify the integrated circuits based on how great gate functionality that these can provide, integrated circuits, and we can classify them into small scale integrated circuits, SSI, that's the small scale integrated circuits, containing between, I believe, 10 to 100 gate level functionalities. 10 to 100 gate level or gates or gate level. So it's a very primitive integrated circuit functionality that will provide you with 10 to 100 gate level functionality. Okay. Next, again, so we are classifying them based on what kind of gate level functionality that these circuits can provide. Okay. Next was the MSI, the medium scale integrated circuit, providing you with 1,000 or 100 to 1,000 gate level functionality. Then you have the large scale integrated circuits. So as things evolved, you are able to pack more and more transistors or gates on the single chip. And then you have the large scale integrated circuits providing you gate level functionality between 1,000 gates to 20,000 gates. Then you have the very large scale integrated circuits or VLSI providing you with the gate level functionality of 20,000 to 50,000. And then you have the ultra large scale, which we are currently having, with the gate level functionality larger than um, larger than 50,000. Okay. And one example of a medium scale integrated circuit is the multiplexers. Okay. Multiplexers. So we're going to talk about the design using the medium scale integrated circuits. Now, you may ask, how do I do the design using the ultra large scale integrated circuits? That corresponds to, utilizing your microprocessor, for example. Your microprocessor is an ultra large scale integrated circuit. And utilizing this microprocessor to obtain the functionality, what you derive, what you desire, right? And this is what is done commonly, especially in the design of embedded systems. You basically have this micro or the design of all the logic that happens in your automobiles, for example, all the control logic, right? When you open the door, lights turn on. When you press one switch, you have all this logic happening all the time. You have various sensors that are integrated on the chip within your car, and this microprocessor is the one, this microcomputer that you have within the car is the one that controls all of those uh, inputs. Okay. And how are you doing that? You're basically programming the microprocessor. In other words, you're obtaining the functionality of the ultra large scale integrated circuit in terms of programming the microprocessor so that it performs what you want it to perform. Okay. But here, let's so that's more of programming, and then uh, obtain the functionality from your ultra large scale integrated circuits. Here, let's focus on medium scale integrated circuits. The same concept, multiplexers, is one example of that. And we will see, again, this is basically a piece of, like you can consider that as a module that is pre-developed, that you can actually buy, that you don't have to develop by yourself. You can actually get them already fabricated as integrated circuits. Okay. Now, the only thing is, again, you don't have access to the individual gates within the multiplexer. However, you should be able to come up with schemes or techniques to obtain the functionality, that gate level functionality, by mapping your function onto that piece of hardware. Okay. So our topic today is on the description of the multiplexer and utilizing the multiplexer in our design. Multiplexer, as you will see, is a very handy piece of hardware or module that you can utilize in your design. So design using multiplexers. Okay. Where can I use them? What is, let's actually talk about what it is in the first place. All right. Now, let's consider this situation or scenario, for example. Okay. We have two inputs, X and Y. And I would like to design a piece of hardware so that I can obtain the functionalities, I can obtain these functionalities from the piece of hardware. X exclusive OR, Y, X and Y, X or Y, and X exclusive NOR Y. Okay. I want to design a piece of hardware that can give me all of those functionalities, okay, that can be configured to be multifunctional, right? So I would like a piece of hardware to be multifunctional here. Multifunctional. The hardware should have one output, obviously I need to have 4 inputs, let's say. And what else do I need? Okay, I have one output and I would like to get all of these functionalities from that one output. So I need to specify the hardware, what output I need. Right? Again, going back to the analogy where we specified how our adder circuit can be configured as an adder/subtractor circuit. What did we use there to be able to configure that adder/subtractor circuit as an adder/subtractor circuit? What specifies how that circuit is configured at any given time. What do you think? If you recall from going back to the design approach that we have taken, we have introduced a concept there. Do you recall what we are talking about here? What specifies, again, adder/subtractor circuits? It's a circuit that can perform both addition and subtraction, okay? And some things I can apply some input to make that or to configure that as an adder at a given time, as a subtractor at a given time. Control, that's right. It's the control unit or the control input. So we need a control input because now I have one output, and and depending on what I apply on the control input, I should obtain any of these functionalities from that hardware. Okay. So control input. How many control inputs should I have now? Because I want to multiplex. So we're already talking about multiplexing. A multiplexer is basically a device that would allow, that would enable multiplexing. So here I would like to multiplex between four outputs or four functionalities here. So I want to multiplex. So that means at any given instant of time, I want to output one of these outputs through my hardware. So how many control inputs should I have? I need to be able to select one among four, right? In the adder/subtractor circuit, I had to select one among two, right? Either I have to select it as an adder or a subtractor. That's why we had one control input. In this case, I have to select one out of four possibilities. So how many control inputs should I have? One out of four, right? That means I have to have two control inputs. And we can specify something like this. Okay. Let's say my control input is S1 and S0. And the possibilities are 0, 0, 0, 0, 0, 0, 1, 1, 0, 1, 1. So let's say for the control input 0, 0, when I apply it on the hardware, I would want X plus X or Y operation to be outputted. So I would like to configure the hardware as an XOR gate, as something that performs an XOR operation. Okay. When I apply a control input of 0, 1, that's my control input. In this case, now I have two control inputs because I have to multiplex between four possibilities. So 0, 1, let's say I want to configure that as X and Y operation. Okay. If I apply a 1, 0 on my control input, I would like to configure the piece of hardware to perform X or Y operation. And 1, 1, I would like to have that operated for function as an X nor Y operation. Okay. So that's how I would define my control input. So now how do I design the hardware? Okay. Now it turns out that the multiplexer exactly does this for us. So what is the multiplexer then? It's basically a piece of hardware. Let's say again it comes in different sizes. You have different sizes for this. So let's say I'm trying to describe a 4-to-1 multiplexer. In short, we can call a multiplexer mux. Okay, a 4-to-1 mux. So what you have is basically four inputs, and you can multiplex among those four inputs. That means you have one output F. Let me call it I0, I1, I2, I3, and then two selector inputs, selector pins, S0, S1. Okay. Now this is a 4 to 1 mux. 4 to 1 mux. What does it do? How does it function? It basically functions as something that can multiplex between the inputs. That's why the name multiplexer, right? You can imagine this as a telephone exchange. Now, depending on, so let's say you have 4 calls, these are the calls waiting here to be connected. You have 4 calls waiting to be connected. That's how, depending on what you apply on the selector inputs here, one of the call is going to be routed to the output. Okay. It's like a telephone exchange where you have 4 calls waiting to be connected. Only one call can be connected to the output. And what determines that one call? What you apply on the selector inputs. So for example, and the way this is configured is S1, S0, F. If I apply 0, 0 on my selector input, then I0, the call that is connected to the I0 is routed to the output. In other words, S1, S0 routes I0, whatever is connected to the I0 to the output. 0, 1 routes I1 to the output. 1, 0 routes I2. 1, 1 routes I3. So that's how my multiplexer functionality is described. Okay, that's how it works. That's how the multiplexer works. All right. Okay. Now, the good thing about this becomes very handy, especially when you want to multiplex. Okay, and oftentimes when you're trying to design a system, digital system, you want to do that. We want to multiplex, right? And this enables you to do that. All right. Now, what I want to do now is I want to design a piece of hardware that can perform these operations. By applying a multiplexer, now I would like to obtain those functionalities from the piece of hardware. Okay. How do I do this? I can directly use that, and I can directly utilize the multiplexer to obtain that functionalities. So let's see how we can do that. Okay. All right. So I take a multiplexer. In this case, this is how I defined. I can directly take a multiplexer here. That's my multiplexer. That's a 4 to 1 because I have 4 inputs and 1 output. Okay. That's I0, I1, I2, I3, S1, S0. That's a 4 to 1 mux. And I would like to get the functionalities. So let's say these are my inputs, X and Y. Okay. Now, these are, so I am applying my control inputs here to the selector pins. So I'm applying my control inputs to my selector pins of my multiplexer. All right. So that means when I apply 0, 0, 0, 0, I should be getting as an output, I should be getting this operation, exclusive or Y operation. So if I want to do that, if I want to get this is what I will do. I would use an XOR gate here. All right. And then I would basically connect these together. That's it. So when I apply 0, 0 on my selector inputs, I0 is the one that is being routed to the output. And what is connected to the I0? X exclusive or Y. So I will get that functionality directly from this. And likewise, I can map the other functions as well. So for 0, 1, I know that I1 is the one routed to the output. What should I apply to I1? An AND operation between X and Y. So here I will apply an AND gate. between X and Y. Same thing. That's X. And that's Y. So now 0, 1 gives me the, on the function, I get the AND operation between X and Y. X or Y, when do I get it? When I apply control input of 1, 0 here, 1, 0. I2 is the one routed. That means I need to apply the OR operation here. All right. Between X and Y. And finally, I need to get X exclusive NOR Y for 1, 1. Right? So let me do that. That's exclusive NOR Y. And here I have. So now with the same piece of hardware, I'm able to multiplex between all of those outputs, right? So my control inputs are applied on the selected pins. Depending on what control input you apply on the selected inputs, only one of the output is routed to the, only one of these inputs are routed to the output. And I can get the functionality as I described in this particular table. So it allows you multiplexing. Okay. All right. So let me take a pause here and let me see if you have any questions on the description of the multiplexer itself. Does that make sense? Okay. All right. So now, that's the major use of the multiplexer is it's basically utilized to multiplex. Okay. Now, as I mentioned before, multiplexers can come in different sizes. So that's a 4-to-1 mux. You can also have 2-to-1 mux. Now, okay. When I say 2-to-1 mux, that means that's a multiplexer that can multiplex between two inputs. All right. So you can imagine the multiplexer to be something like this. So that's a 2-to-1 mux. Would basically consist of a multiplexer, something like this. How many selector inputs should I have for the 2-to-1 mux? That's a 2-to-1 multiplexer. So you're multiplexing between I0, I1. How many selector inputs should I have? Only one, right? So in this case, I have S0 as the selector input. And what you apply on the selector input, one of the inputs are routed to the output. So that's the 2-to-1 mux. Similarly, you have 8-to-1 mux, in which case you have 8 inputs. How many selector inputs? For an 8-to-1 mux, again, you're trying to multiplex between, that's exactly right. Selector inputs equal to 3. So your 8 inputs goes as I0 through I7. Your selector inputs goes as S2, S1, S0. Right? I 8 different possibilities. So 0, 0, 0 is S0, 0, 0, 1 is S1, 1, 1, 1 is S7. So I have 8 different possibilities, and what you apply on the selector inputs, the corresponding inputs are being routed to the output. Yeah. How do I construct a multiplexer? It's actually pretty simple. Yeah, let's actually do it for a 4-to-1 multiplexer, and then you can extend the concept to any other multiplexers. Constructing one. Constructing so when I say constructing, what I mean is how do I construct a multiplexer using fundamental gates? Okay. A 4-to-1 mux. Again, this is how the mux should operate. S1, S0, 0, 0, 0, 1, 1, 1, 1, 0, 1, 1. That's your output. I1, I2, I3, I4. sorry, I0, I1, I2, I3. I1, I2, and I3. Okay. All right. So how do I construct one? I can write my F as I0 times S1 prime S0 prime plus I1 times, so I'm trying to write you can think about these as minterms corresponding to each of these combinations. Minterms corresponding to, okay, let me solve the minterms. Corresponding to S1 S0 0 0 is basically S1 prime S0 prime. Minterm corresponding to 0 1 is S1 prime S0. Minterm corresponding to 1 0 is S1 S0 prime. 1 1 is S1 S0. Again, call that the minterms because these are unique, and only for this particular for example, this particular minterm is unique to this combination because only when I enter these values 0 0 into this, I get a 1 as the output of the of the product term. When I put these 0 0 in any of the other minterms, that should produce a 0, right? So now I write f as a function of minterms along with I0. In this case, so f is I0 times S1 prime S0 prime plus I1 S1 prime S0 plus I2 S1 S0 prime plus I3 S1 S0. So this is how I would implement my multiplexer. Would it work? You can substitute the values of S and see what you get, right? If I substitute 0 0 here into this expression, what am I going to get left behind? If I substitute S1 equal to S0 equal to 0, what becomes my F? Again, because S1 is equal to S0 equal to 0 is this combination, the minterm corresponding to this combination is the only one that provides a 1. So that's the only one that going to provide a 1. So I'm left behind with I0 times 1 plus all zeros, right? Because everything else goes to 0. So I'm left behind with I0. And you can check for other combinations. Let's say, substitute S1 equal to 1, S0 equal to 1, which corresponds to this minterm combination that provides a 1 at the output. And everything else goes to 0 except the last term, because 1 times 1 is 1, and I get my function f as I3, and so on. So that's how I can implement a simple multiplexer, right, at the fundamental gate level. But of course, that's something that you should know. But you don't have to implement your own multiplexers now, because you can actually use that as modules because they're provided to you as well-defined modules. Okay. All right. So that's good. I hope that makes sense. Does that make sense? Any questions here before we move on? So now we have seen how we can use the multiplexer in our design to multiplex between different operations. What is the internal construction of a multiplexer? So if I want to look inside how it is constructed at the fundamental gate level, that's what you would see, the innards of the multiplexer. Okay. And now what I want to do now is, can I obtain any function instead of directly using fundamental gates? Can I utilize a multiplexer and obtain any function? Okay. The simplest function, not just any function, but the simplest function. Let's see how we can do that. In this case, you're trying to map the function, any function, onto the pins of a multiplexer. So you're not directly utilizing the gates, but you are utilizing the gate level functionality that is offered by the multiplexer in being able to map your function onto the multiplexer. Okay, so this is what I would do. Okay, so the problem statement here is design. Let's say design a full bit adder using a multiplexer or using multiplexers. So let's say you're asked to design this with multiplexer and minimum number of external gates. You want to minimize the number of external gates. How would you do that? So obviously here I would like to utilize the multiplexer to my advantage and see how we can do this. Okay. Now, so let's again going back to the first, of course, I start with the truth table for this. The truth table for this, again, remember that this we had for the full adder, we had the Ci minus 1, we have three inputs, Ci minus 1, Ai, Bi as the inputs, and then we have two outputs. Because I have two outputs, a single multiplexer can only provide me with one output. That means I have to use two multiplexers to realize this circuit, the entire circuit, right? So here I have Ci, Si, okay? And let me finish this. So this is something that you already know. We have done this before. 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. And you know what the outputs are. So basically you're adding 0 plus 0 plus Ci minus 1 plus Ai plus Bi for each input combination. So here I have 0, 0 as the output. Here I have 0, 1. Here I have, again, 0, 1. Here I have 1, 0, because 1 plus 1 is 1, 0. Here I have 0, 1. Again, 1, 0. 1, 0. 1 plus 1 plus 1 is 1, 1. So that's what I have. Okay. Now this is what I want to implement, not by using the K-map approach, but I want to use it. I want to utilize the multiplexer into the picture. So how do I do this? Okay. Let's first focus on implementing Ci. Okay. All right. So I want to implement that using a 4-to-1 multiplexer. So I need to specify what multiplexer I'll be using. Try to implement that using a 4-to-1 multiplexer here. And this is how that would look. That's a 4-to-1 mux. I0, I1, I2, and I3. S1, S0. That's your function. So now here, I know what the function is. This is what the function is I want to implement. And I want to map my inputs. Again, remember that the only things that are accessible to me as a designer at this stage are these pins. These are the pins, right? These are the pins. These are the input pins of the IC. So basically, you can think about this as an IC chip that you can buy, the integrated circuit that looks something like this. The IC package that you can buy and solder it on your PCB. Remember? So these are the pins that are available to you. You cannot really go into that device itself. You work with those available pins. So those are the pins. Those are the input pins. And that's your output pin available to you. And that's it. And you have to map your function onto those pins in the right way. Okay. And now we're going to see how we can do that in a more systematic manner. Input and output pins. All right. So what I will do is this is the approach I'm going to take. First, I will define what I will be applying on my S1 and S0. Okay. Obviously, these are the inputs. These are the inputs. So obviously, I have two inputs here. I will choose two of the inputs from my truth table and apply on my input on my selector inputs. So first, choose, in this example, two inputs of the function to be implemented and apply them on the selector inputs. Apply them on S1 and S0 inputs. Okay. Let me say I will apply AI and BI, okay, on my selector inputs. So I am applying AI and BI. Let me see. Let me actually do one thing here, just to make it obvious, make it easy to see. I'll call this AI, call this BI, call this CI minus 1. Nothing changes. The truth table, the CI and SI doesn't even change. That doesn't really change, even if I change these values. Okay, so that's still valid. Okay, so applying AI and BI, two of my inputs of the function on my selected inputs, AI and BI. So that's the first step I will do. Okay. Now, once I fix this, once I fix these inputs, what inputs I'm applying here, what I should be applying here, I0 through I3, are functions of the rest of the inputs. Okay. So the second thing is, once S1 and S2 are fixed, I0, I1, I2, I3 are functions of the rest of the inputs, rest of the function, rest of the inputs. That means, what that means is, you do not expect AI and BI to be appearing again here. Once you have fixed this, AI and BI are fixed. You cannot expect these to be appearing again at these terminals. Very important. All right, so how do I map this design? Okay, now I've applied AI and BI here. Again, how does this multiplexer work? S1, S0. In this case, my S1, S0 corresponds to AI and BI, right? Because that's what I applied on my S1, S0. And the function f. So 0, 0. So when I apply 0, 0 on my AIBI, that means I'm applying S1, S0 as 0, 0. What is routed to the output? I0. Okay. Are you able to see it? Okay. Zero, 1, 0, 1. I1 is routed. 1, 0, 1, 0. I2 is routed. 1, 1, 1, 1. I3 is routed. Okay. All right. When I apply, so if I go back to this truth table, so these are the situations where I apply, where my AI and BI are both zeros, right? Now relate that to the function. I want my f to be Ci here. I'm trying to implement for Ci. In the first case, I want my f to be Ci. Okay. All right. When I apply AI and BI to be 0, zeros, 0, zeros, I want my f, this is my f for now, the output of the multiplexer, to be Ci. Okay. So what should I apply? Of course, when I apply 0, 0 here, what is being routed to the output? I0. I0 is the one that is being routed to the output when I apply AI and BI to be 0, zeros. That means to match the function description for Ci, what should I apply on I0 so that this truth table is uh, what do I say? Satisfied. I hope you are able to understand until this point. Okay. I fixed AI BI to be 0, 0 in the first case. When I fix AI BI to be 0, 0, I0 is the one that is being connected to the output. It is being routed to the output. What should I apply on I0 so that I can get the right function Ci? Go back to the truth table. When I apply AI BI to be 0, 0, as I mentioned before, I0 is the function of the rest of the inputs only. So this is fixed. I0, my function output f, is a function of the rest of the inputs. So I0 should be a function of Ci minus 1 only. So what should I apply in terms of Ci minus 1 to I0 to get the right function? As you can see here, Ci is 0, Ci minus 1 is 0, Ci is 0, they correlate. Ci minus 1 is 1, Ci is still 0. That means when I apply 0, 0 as my inputs on my selector inputs, independent of Ci minus 1, my function is equal to Ci, right? Independent of is equal to 0. Independent of Ci minus 1, whatever you apply here, it should be whatever is the value of Ci minus 1, the function should be 0. In other words, I should apply a 0 here so that this condition is satisfied. When Ai and Bi are zeros, Ci is 0. Doesn't depend on Ci minus 1. Okay, let me take a pause here. Let me see if you actually understand that. Does that make sense? Any questions on this part? Okay. I have not used Ci minus 1 because I did not have to use in this particular example. That's because my output Ci, when Ai and Bi are both zeros, is 0. Whether Ci minus 1 is 0 or whether Ci minus 1 is 1, it doesn't matter. It's 0. In other words, when I apply 0, 0 here and a 0 here, then my function, I get the right function equal to Ci. Because when I apply 0, 0 here, I0 is the one routed, right? And irrespective of what you apply in Ci minus 1, I obtain a function Ci equal to 0. Does that make sense? Let's look at the other example, other instance where I'm applying on my selector inputs. Okay. 0, 1. So I'm applying 0, 1 on Ai, 0 on Ai, 1 on Bi, which corresponds to this situation. That means I1 is being routed to the output. So that means I need to apply the right function here so that I get the right output. And this is the situation where we see that. My Ai and Bi, my Ai is 0, is that right? No. Yeah, my Ai is 0, Bi is 1, so that corresponds to these instances. What is my Ci? Now what I have to apply here depends on Ci minus 1 only. And I can see here, right? When Ci is 0, for this particular situation, when Ci minus 1 is 0, my Ci is also 0. Ci minus 1 is a 1, Ci is also 1. So what do you think should be applied on I1 to get the right, so this corresponds to this truth table? What should I apply on I1 then? In this case, I1 should be a function of Ci minus 1 only. And what should I be applying on I1 to get the right output corresponding to this function, to that truth table? Ci minus 1. In other words, if I apply Ci minus 1 here, when Ai and Bi are both 0, 1, when Ai and Bi is 0, 1, I1 is being routed to the output. When I1 is routed to the output, that is, if I apply Ci minus 1 on I1, then my Ci, I will get the right Ci. Okay. All right. Let's look at the other possibility now. 1, 0. 1, 0 on Ai, Bi, that means I2 is the one routed to the output. So this corresponds to I0 that is routed. This corresponds to I1. This corresponds to I2. And this corresponds to I3. Right? So I2, AI1, BI0, I2 is the one routed to the output. And what should I apply in I2? I2, which is a function of Ci minus 1 again. Okay, I see that my Ci is nothing but Ci minus 1. If my Ci minus 1 is 0, under this situation, Ci is also 0. Ci minus 1 is 1. Ci is also 1. Right. In other words, just like what I've done here, I can basically short them together, apply Ci minus 1 on both of those inputs, I get the right output. Okay, so I'm done with 1, 0. Let's do for 1, 1. 1, 1 corresponds to this situation. That means my I3 is the one routed to the output. And again, my I3 should be a function of Ci minus 1 only. And how does it depend? Again, here, my Ci, that's the output of the function, is 1 if Ci minus 1 is 0, is 1 again if Ci minus 1 is a 1. What it means is it does not depend on Ci minus 1. Irrespective of what you apply here, irrespective of what you apply on Ci minus 1, under this situation, my Ci is simply 1. So what should I be applying on I3? From the truth table, when Ai and Bi are both 1s, the output Ci does not depend on Ci minus 1. It's 1 either ways. So yes, that's correct. I should be applying a 1. That's it. And now I've realized this function without using any external gates. I've realized the function, right? Just using the multiplexer. Just by mapping my function onto the input pins, input output pins of the multiplexer. And that's the procedure you will follow. First, fix what you want to apply on the selector inputs. Once that is fixed, then your other inputs of the multiplexer depends only on the rest of the inputs of the function. That's how you would obtain. Let's finish this problem. Let's similarly, let's do it for SI as well, so that we completed. And we should be able to do that quickly now. Now that we know the procedure, we should be able to do that much more quickly. I0, that's another multiplexer we are using to obtain this S0, SI. In this case, I'm mapping my output to the output of the multiplexer, SI. Again, to be consistent, I'm applying my AI and BI as my selector inputs. And now I want to obtain my SI. So in this case, again, I0 through I3 are functions only of Ci minus 1 now. And let's see the dependence now on Ci minus 1. When I0, when AI, BI are both zeros, that corresponds to this condition. When my Ci minus 1 is 0, Si is 0. Ci minus 1 is 1, Si is also 1. So what should be applied on I0? Ci minus 1. Perfect. Similarly, we'll do for I1. For I1, which corresponds to this, because I'm applying 0, 1 on my AI, BI. Ci minus 1, my Si is 1, when my Ci minus 1 is 0. Si is 0, then my Ci minus 1 is a 1. What should be applied on I1? Ci minus 1 prime, exactly. Perfect. So in other words, I can probably invert that, apply it here. I1. I2, which corresponds to this, applying 1, 0 on my AI, BI. Si is 1, when my Ci minus 1 is 0. Si is 0, when my Ci minus 1 is a 1. Right? So in other words, I should be applying again the same thing, Ci minus 1 prime, so I can just do this on I1 as I2, right? Because that's complemented. And finally, for I3, Si is 0 when my Ci minus 1 is 0. Si is 1 when my Ci minus 1 is also 1. In this case, my Si is the same as Ci minus 1. So I will have to, I guess, invert this to get back Ci minus 1 and apply to I3. Or if I don't want to use another gate, I'll probably just take that and apply here. Either ways. So now I have realized both my Ci and Si using multiplexers with the use of a minimum number of external gates. I'm not really using a lot of external gates. I just realized my function. Okay. All right. Does that make sense? Any questions on this so far? So that's how you can build your functions. Okay. So again, this, when I say adder, right? An adder, a single bit adder circuit has two outputs and three inputs. Right? In this case, I have AI, BI, CI minus 1, and SI, and CI, and SI. Right? So if I want to, so this is what we wanted to design. And so these two circuits, even though they look independent, form the same circuit here. So basically, within this device, within this unit, I would have two multiplexers, functions of these common inputs, providing me two outputs, CI and SI. Okay. That builds a single bit adder. And now, if I want to make it into an n-bit adder, of course, you can connect multiple ones as we have seen before, right? Does that answer your question? Yeah, sure. I1 again for CI minus 1. Okay, so the question was, let me see, or I1 again if you don't mind. For CI, okay, CI, I1. Okay. So for this particular case, when I apply 0, 1 on my AIBI, 0, 1, I1 is the one routed to the output, right? 0, 1, okay, you can think about it as a binary value. 0, 1 is 1, 1 being routed to the output, okay? Now, 0, 1 I'm applying here. So those are fixed, okay? Now, this output is CI here, okay? When I apply 0, 1, what should I be applying on I1 to get the right CI? All right? What should I be applying on I1 to get the right CI? How do I determine that? I would determine that from this truth table. So because these are fixed, let's not worry about this for now. Just ignore them. I fixed them. Now my CI only depends on CI minus 1, right? Because that's the only other input that we have not considered. These are fixed here. This is not really fixed yet. This, what we apply here depends on CI minus 1 only, right? Now, what should I be applying on this? Again, going from the truth table, to get the right CI for this condition. So CI is a function of CI minus 1 only. And in other words, I should be applying here some function of CI minus 1. What should I be applying so that this condition is satisfied? So I will go back to this truth table here and see that I observe that CI is 0 when CI minus 1 is 0. CI is 1 when CI minus 1 is 1. That means my output follows this input now. It's dependent only directly on CI minus 1. So that's why if I apply CI minus 1 directly here, then when I apply 0, 1 here, that becomes, something like this. So my truth table would become something like this. So A and B are fixed, AI, BI are fixed, right? And my function, I'm applying CI minus 1 here, my function becomes CI minus 1, right? Does that make sense? If AI, BI are fixed, applying CI minus 1 here, I get CI minus 1, okay? And what should be CI? CI is nothing but CI minus 1, right? So by applying CI minus 1 on I1, I get the right function. right? Function ci. Okay. Esteban. So multiplexers can only handle one output. Okay, multiplexers can only handle one output. That's correct. It's always one output. You're always multiplexing between multiple inputs, and among those multiple inputs, you're selecting one to be routed to the output. So it's always one. Okay. So you can have 16 to one multiplexer, but again, you have 16 inputs. Among those 16 inputs, you're taking one output, one for the output. All right. Fabian, does that make sense, the explanation why we applied Ci minus 1 here? We want to, whatever we apply here, this should be corresponding to this truth table. This should make sense. We should be getting the right output, right? Okay. We'll take more examples, and hopefully that will also improve your understanding. Okay, so this is how you can do it directly from the truth table. The other way that you can do this is through the K-map approach again. So we'll modify the K-map a little bit, but otherwise everything else remains the same. So now we have looked at a simple example. Let's take another example where we are given a function. Let's say you're given a function f. In this case, you have a function a, b, c, and d. You have 4 inputs, and the function is given as sigma m 1, 4, 5, 7, 9, 12, 13. 1, 4, 5, 7, 9, 12, 13. I want to implement that using a 4 to 1 multiplexer. And I want to do that using the K-map approach this time. So let's see how we can do that using the K-map approach. Again, very similar in principle to what we have just seen. Okay. So let me draw the K-map for that first. So the K-map that corresponds to that function is something like this. Have 4 inputs, 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 0. And then I have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay. All right. For now, let me put also zeros here in the rest of the places, and we'll see why. Okay. And I want to implement that function using a multiplexer and minimum number of external gates. So that's a 4 to 1 mux. And I have S1, S0. And those are the inputs of the multiplexer, I0, I1, I2, I3. Okay, and that's the output. F. Similar to what we have done before, we'll choose 2 of the inputs here from here and fix them to be applied on S1, S0. We'll fix them. The important thing is we need to decide what input should be applied, what input should be fixed, because that will determine the complexity of the circuit. And that's hopefully that will, in this case, that will illustrate that. So let's say, for example, I would like to fix A and B here. So I take A and B as my inputs, fix them here. What that means is what I'm applying here for the other for I0 through I3, those are going to be functions of only C and D, because A and B are fixed. What I'm going to apply here are going to be functions only of C and D. In what way can I determine what should be applied? Right? I can do that using this K-map. What I will do now is I will divide this K-map into sub K-maps. Okay, this is how I would divide it in this case, because I'm using A and B as the selector inputs. My A and B is constant across this entire row, right? 0, 0, value of A and B is 0, 0 is constant across this entire row. A and B value of 0, 1 is constant across this entire row. 1, 1 is constant across this entire row. 0, 1, 1, 0 is constant across this entire row. So I would divide this K-map into these rows, individual rows. Each of these individual row now functions as an individual K-map now. So those are my individual K-maps, or you can call them sub K-maps. I will use the exact same rules that we have derived for the K-maps, but on the individual rows only. Why am I doing this row-wise? Because I'm using A and B as my selector inputs. A and B values do not change along these rows, right? When I apply A and B of 0, 0, what is being routed to the output of the multiplexer is I0. So whatever function I get in terms of C and D from this K-map should be applied to I0. A and B of 0, 1 corresponds to I1. So whatever function I get from this sub K-map should be applied to I1. A and B of 1, 1 corresponds to I3, right? 1, 1 is 3. So whatever function I get from this should be applied to I3. Oh, yeah. And 1, 0 is I2. And whatever function I get from this sub K-map should be applied to I2. Okay. Now, if I had chosen C and D as my input pins, as my selector inputs, how would I divide my K-map then? I could have done that too. In fact, we should do that. If I had done C and D as my selector inputs, how should I divide my K-map to sub K-maps? Vertically. That's absolutely right. Columns. Because my C and D values are constant across the columns, so I would be dividing my K-map into columns then. All right. So for now, let's do that. And now I would combine the ones exactly the way we have done for the K-maps, right? So, but the only difference here is I would view this column, individual column, as the K-map itself. So how would I combine here? The only way I can combine here is this. That's the only way, right? Now, what is the product term? Now, my product term should be in terms of C and D only because A and B is already accounted for here. So from whatever product term I'm going to get from this K-map or the sub K-map should be in terms of C and D only. So what is the product term in terms of C and D? That's C prime D. That's C prime D. Right? So if I apply C prime D here on I0, then my A and B are 0, 0. I0 is the one routed to the output. If I apply C prime D here, I'll be getting the right function F. Because my I0 is a function of C and D only, and it's a function, more explicitly, it's a function of C prime D. As long as this condition is satisfied, I'll get the right function. For AB 0, 0, my output of the multiplexer F is I0, which is basically C prime D. Okay. Now AB of 1, 0 or 0, 1. In this case, again, that's my sub K map. I'll combine these two adjacent ones along with these two adjacent ones and read out the product terms in terms of C and D only. So I have two product terms. In this case, that corresponds to what? C prime. That's C prime. And this product term corresponds to D. Right? So the function I get from the sub K map is C prime plus D. And that's what I'm going to apply here, C prime plus D. Why? Because when I apply 0, 1, when I fix my selector inputs to be 0, 1, then the function f is I1. And what is being applied is C prime plus D, this function, and then I get the right function corresponding to this. 1, 0. 1, 0 is this. That's the combination, which is, we have already seen that's C prime D. 1, 1. 1, 1. So that's this combination. So I2 is one that is routed, and I2, I'm applying I2, C prime D. Then 1, 1. I3 is the one routed to the output, and as long as I apply, wait a minute, I3, yeah, I3, as long as I apply C prime, right? C prime on my I3, I get the right function. All right. A good exercise for you guys now moving forward is to see what if I've chosen C and D as my selector inputs. If I chose C and D as my selector inputs, my I0 through I3 are functions only of A and B. My columns become the sub K maps. Perform the combinations and compare your result, your function for the multiplexer. Are you using more gates than this or less gates than that? And you will realize that what you select as your selector inputs really matter, because that determines the complexity of your final circuit. Determines complexity in terms of how many external gates you need to realize the final circuit. Okay. All right. Let me pause here and let me take any questions you may have. Does that make sense? Does the approach make sense here?
So for the C prime D column, where you have 4 1s in a row, if we
Four
were to
ones in a
fix
row. I don't have 4 1s in a row, right? Oh, you column, you mean column, yeah.
in the column, yeah.
Yeah. 4 1s in a row, okay.
If we were to fix C and D, like you said for the exercise, we would then combine all those 4, right? Because that's the biggest possible
That is correct.
combination.
That's correct.
Okay.
So that's a K map full of ones. What does that function is? How can you write that function as?
It would just be 1 then, right?
It's 1, absolutely. So in other words,
Okay.
for this particular condition, you will be applying 1 on what terminal? 0, 1, right? 0, 1, that means I1. So you'll be applying a 1 on I1. Does that make sense?
Yeah.
Okay. Any other questions, guys? If not, then that's it for today, and you guys have a good weekend. I'll see you guys on Tuesday